In this talk, in contrast to the first two, I'll probably be going at a more leisurely pace. There are roughly 3 parts to this talk. The first part is to look at the Artin-Mazer zeta function for unlabeled graphs and their adjacency matrices over Z+. This really is just a warm-up act. Well, of course, maybe in this room we need a warm-up act. And it's, let me see, where's the button? Okay. For Mark Polikoff, that's the main event, and he will tell you a lot about a variety of zeta functions. So this is a little bit of a warm-up. I'll more slowly do some elementary formal aspects of this Artin-Mazer zeta function and apply it to just one case in which we use the function to encode the number of length n loops in a directed graph with their weights if the graph is a labeled graph. So I apologize to those of you who already know this quite well. Anyway, this kind of zeta function for a directed graph will also be a step to connecting to a more refined kind of algebraic invariance away from 0 for a matrix, something more refined than the non-zero spectrum and eventually much more refined. And that's one reason why I'll emphasize that this zeta function as a formal, can be viewed as a formal power series regardless of convergence issues. Okay, so for a matrix over a more exotic ring, it's good to begin with something that's defined independent of ideas of convergence. But if you don't share this fetish for algebra and you prefer honest functions of a complex variable, don't worry. Help is on the way. Okay, so let's start with a little bit of formal abstract nonsense, not very abstract. So we'll consider a formal power series. Now, a formal power series is basically an infinite series viewed as a polynomial. So we just have a sum here, and I'm considering a power series which has a 0 constant term. And if I have such a series with a 0 constant term, I can plug it into, for example, the power series for the exponential function, and I'll get another well-defined formal power series. Now, why is that? Well, what does it mean to have a well-defined formal power series? It just means that I have to be able to compute the coefficient of z to the n for every n. And if I look at this formula here, well, I can see that if I am interested, let's say, in n equal 10, the terms which involve powers higher than 10 will involve powers of z that have no relevance to that coefficient of z to the 10. So it's really enough to just look at the polynomial up to degree 10 and plug that into the exponential series. And again, I only have to look at, I can truncate that series at degree 10 too. And so really I'm just making a computation with polynomials. Okay. So this is well defined. If I had a non-zero constant term, then I'd start getting into trouble because I'd be adding it repeatedly, and that wouldn't make sense anymore. Okay, so this makes perfectly good sense. And well, likewise, suppose that I take this exponential with this series plugged in. Well, the exponential is 1 plus whatever's left. I'll let w be the series, which is whatever's left. I could use the familiar series for the log of 1 plus w and just plug w into that series. Okay, and I'll get another power series. And this will be a well-defined formal power series. Okay, so we can do these computations really without worrying about issues of radius of convergence. these familiar equations we know are true for polynomials within some radius of convergence. But, because that's true, behind that there have to be combinatorial identities of the power series coefficients, which give the equality of the formal power series independent of the convergence issues. On the other hand, if you like, you can go figure out what those identities are and go prove them and just do this directly. Okay, so consequently, we can think of this series, the exponential of the series alpha of z, as a way of encoding the series alpha of z. Each of these series determines the other. And the common... Okay, so now why might one be interested in this encoding? Okay, well, now we come to this artan Maser zeta function. Suppose that we have T, which is a map from some space, some set even, to itself. And, well, T to the n is just going to be the n-fold composition. So, T1 is T, and Tn is Tn minus 1 composed with T. And now suppose that for every n, T to the n has only finitely many fixed points. That's all that we're going to need to have a well-defined function. The artan Maser zeta function is given by this formula. We have the exponential, and into that exponential series we substitute for the variable this other power series. This other power series is as the series in which z to the n has the coefficient, the number of fixed points of t to the n divided by n. Okay. And this is well defined. And so this zeta function encodes the whole sequence as we've seen, which is given by the coefficients of this series we're putting in. And of course, if you know the number of fixed points divided by n, you know the number of fixed points. So this is a way of encoding the sequence, which is the number of fixed points of the nth power of t for all n. Okay, now if you've never seen this before, and I hope some of you at least have never seen this before, this might at first glance seem to be a rather peculiar choice to use. Why not just stick with the original sequence? Well, there are a lot of good reasons, and you'll see a lot more this afternoon. But let's start to see some kind of rationale now. Okay, so it's always good to start with the fundamentals and then work your way up. So let's look at the zeta function for a system which is just one fixed point. Okay, and well, what would that zeta function be? Well, let's go back. You can see the. Oops. Let's try to go back again. Okay, so in this case, well, the number of fixed points for t to the n is just 1. There's nothing else in this universe but one point, which is always fixed. So, so we have this zeta function, and well, let's just do the elementary exercise. This series is 1 over 1 minus z. It's 1 plus z squared plus z cubed, etc. Okay, and well, let's just check that. Let's take the log of both sides. So we erase x on the right side, and on the left side we have, I haven't lost a sign, the log of 1 minus z, right? And the log of 1 over 1 minus z is minus the log of 1 minus z, of course. And then we can differentiate, and we get the geometric series on the left. And sure enough, on the right side we get 1 over 1 minus z. So so now we can reverse these steps, and the anti-differentiation is fine here because when z is 0, both sides are 0. Okay, so that's the elementary computation for a fixed point. Okay, well, now a finite orbit. So suppose that we have a t, and t is just a cyclic permutation of k points. Well, it's a cyclic permutation of k points, so if n does not divide k, there is no fixed point for t to the n. Okay. On the other hand, if we're looking at a power of t which is a multiple of n, then every point is fixed. So we have k fixed points. Okay, so now we're only looking at those, the only terms in this series which have non-zero coefficients are the terms which are a multiple of n. So we're looking at z to the kn over kn, and in each of those cases the number of fixed points is k, and so that's our zeta function in this finite case. And well, of course we can cancel k. This series is x sum z to the k to the n over n. We see that's the same series we had before, but with z to the k in place of z. Okay, so this is 1 over 1 minus z to the k. Okay, so that's the case of a finite orbit. Well, actually, now we basically have the general case. So let's just see how that works. It works by the product formula. So let's suppose that we have now, we're in this general case, we have t from the space to itself, and it has only finitely, each power has only finitely many fixed points. Okay. Well, let's see, these fixed points of powers are the periodic points, and every periodic point of t has some least power, least period, which is just the size, the cardinality of its orbit. And its orbit is just the set of all iterates under the map T. Well, let's let pi of k denote the number of orbits of cardinality k. Okay. Now, a point's a fixed point of t to the n if and only if it lies in an orbit of size k such that k divides n. Okay, so the number of fixed points of size of t to the n is just the sum over k of the number of points of least period n. So this is the sum over k of k times the number of orbits of size k such that k divides n. Okay, so the sequence of fixed points actually then will determine the sequence pi of n. We can recover it from the sequence of fixed points with the Möbius inversion formula. Okay, so from the dynamical point of view, it's the sequence which is the sequence of numbers of orbits of size n, which is really the fundamental thing. These are the dynamical items. But typically it's the sequence of cardinalities of fixed points, which is more tractable, easier to compute, even often algebraic in formulation. Okay. So the product formula for the Artin-Mazer zeta function is one facet of the way that this zeta function relates to the dynamical sequence, the numbers of orbits, with the sequence which is the number of fixed points of powers. So here's the product formula. On the left side, we just have the definition of the zeta function. And on the right side, we have an infinite product. It's the product over n of this 1 over 1 minus z to the n to the power pi of n. So you can see on the right side, we've just taken each orbit. Each orbit contributes a factor of 1 over 1 minus z to the n if n is the size of the orbit. Okay, so why does it hold? Well, of course, it holds for finite orbits. Okay, and well, Now suppose it holds for a single finite orbit. Now what about finitely many orbits? Well, on the right side, we can take a product of these orbits. We know that would be equal to the product of the zeta functions on the left side. That's going to be a product of exponentials. And we have a kind of familiar fact about the exponential function. E to the a times e to the b is e to the a plus b. And that's going to make this work for a finite product. And then it works for the whole countable product just by the nonsense of formal power series. You know, for the computation of any particular coefficient in the series, that computation only involves terms of bounded degree. There are only finitely many terms involved. So because this works for polynomials, because this works for finite products, it works for infinite products. Okay. Okay, so once we've got the in this formalism, getting this zeta function for a finite orbit just determines everything else. Okay. All right. We broke up our system as a, we got this product formula for zeta functions over individual orbits. Well, if we have, a pair of disjoint systems, and we take the system which is the disjoint union, the zeta function for that system is just going to be the product of the individual zeta functions by the same logic. Okay, anyway, now let's prepare to consider an example for which we can compute this zeta function quite nicely. So, so again, I apologize for those of you for whom this is too elementary. I'll try to be more confusing tomorrow. So let's recall the adjacency matrix of a graph. And when I say graph, I always mean directed graph, unless I say otherwise. And I'll let the bold n be the set of positive integers. Z plus is the set of non-negative integers. So I'm using the American convention here that the natural numbers are the positive integers, and not the French convention that they're non-negative integers. I had to reflect. For some time I thought this was good, but then I come here and I see floor 0, and I think, well, maybe there's a sort of better mathematical culture in the country of France. 0 is more natural. Anyway, so now let's suppose that we have an unlabeled graph. It's got a vertex set, 1 through n. Its adjacency matrix is going to be the n by n matrix, whose entries are defined by setting aij to be the number of edges from vertex I to vertex j. So if we had this graph, think of vertex 1, vertex 2, the adjacency matrix would be that matrix. Okay. Now, of course, we could make another choice of names for these vertices. I could have named 2, 1 instead of 1, 2. And if I did that, then I would get a matrix which would be conjugate to this by the permutation matrix corresponding to the different change of names. And that difference in the matrices is never going to matter for us, and so we'll just ignore it. All right, so counting paths in the graph. Well, suppose that we have this unlabeled graph with the adjacency matrix A. And, I want to claim that for any vertices I and j, and any positive integer n, the number of paths of length n from I to j is just the nth power of the matrix evaluated at ij. Well, if n equals 1, this is certainly true. The number of paths from 1 to 2, for example, is just the number of edges, which is 2. Okay, so if n is greater than 1, we prove it by induction. If n is greater than 1, what is a path of length n? From I to j, it's a path of length n minus 1 to some place, to some k, followed by an edge from k to j. Okay? So, well, so we can count these paths by adding up over k the number of possibilities. So we're adding up over k the number of paths from I to k times the number of edges from k to j. And by the induction hypothesis, we see that from matrix multiplication, this is simply a to the n in entry ij. Okay. And, well, a path in this graph is a loop if it begins and ends at the same vertex. And the number of loops of length n is the sum over the vertices I of the I entry of a to the n. In other words, it's just the trace of the nth power. Finally, a loop's minimal if it's not a concatenation of a smaller loop. A minimal loop is allowed to be a concatenation of distinct smaller loops. Okay, so now we arrive at the zeta function of a directed graph. So there's an important class of dynamical systems and shifts of finite type which are presented by unlabeled graphs or equivalently presented by their adjacency matrices. So I'll consider GA an unlabeled graph, and I'll let T be the corresponding shift of finite type. Now, all we need to know at this moment about shifts of finite type is that the number of fixed points of the nth power of the shift of finite type is equal to the number of loops of length n in the graph. Okay, so I won't say anything more, but for more, there we go. That's right. All right. But so let's go ahead and compute the zeta function for this shift of finite t associated to the matrix A. Now, you can also, and again, you can just think of this zeta t, this zeta function, if you like, as something that's just associated to the undirected graph with adjacency matrix A, since it's just defined in terms of the number of loops of length n in the graph for all n. And there's a famous zeta function, the Ihara zeta function of an undirected graph. This is not that. Okay, so let's compute. And now we'll start to see how the formalism of this zeta function works out very well. We want to compute then, exponential of a certain series. There's the series. And the number of fixed points of the nth power by declaration is the trace of a to the n. It's the number of loops of length n in this graph. Okay, so here's what this function is built to work with very well. Now, the trace of the nth power is, of course, just the sum of the nth powers of the roots of the characteristic polynomial repeated with the correct multiplicity. So there we have that sum. Well, x of the sum is product of the x, so we can pull this sum and write down a series, one for each instance of a lambda in that formula. So we have a product of x, lambda to the n, z to the n. Well, lambda to the n, z to the n is lambda z to the n, and we see that once again we have this the series that we compute very easily. This is the product over lambda of 1 over 1 minus lambda z. Okay, same thing as before. And of course, the product of the reciprocals is the reciprocal of the product, so we have the reciprocal of a certain polynomial. Okay, well, it's pretty easy to analyze this polynomial, so let's do it. These numbers are the roots of the characteristic polynomial of A, repeated with the correct multiplicity. Okay, so let's look at this product. Now I can do a multiplication. So this is one proof which really is not a hand-waving proof. Right? So this polynomial on the left is z to the n times the polynomial on the right. Okay. And, well, we can recognize this polynomial on the right. If we had z instead of z inverse there, we'd be looking at the characteristic polynomial of the matrix. Okay, so this is z. This altogether we have z to the n times the characteristic polynomial with the variable z inverse. Okay. If you haven't seen it, well, let's just see that you can look at this as the characteristic polynomial of the matrix written backwards. Suppose that the characteristic polynomial is z to the n plus some other terms. And let's just chop it off at the last non-zero term. If the characteristic polynomial has 0 as a root, then this last term won't be a naught. Okay, then with this, let's see what z to the n times the characteristic polynomial evaluated z inverse becomes. Okay, so here's z to the n, and to the right I substituted 1 over z for z in the characteristic polynomial. And it's very simple what happens, I hope. Okay, we're just basically writing these coefficients backwards. Okay, and what are the roots of this polynomial, which is the determinant of I minus EA? Well, they're just the reciprocals of the non-zero roots of the characteristic polynomial repeated with the correct multiplicity. The number of zeros plays no role here. As you can see already, 1 minus 0 times z is 1. So, when lambda is 0, 1 minus lambda z plays no role. Okay. Okay, so just to let's look at an example. If A is a 1 by 1 matrix 2, the characteristic polynomial is z minus 2, and the determinant of 1 of I minus EA is 1 minus 2z. Okay, if the characteristic polynomial is z to the 6th minus 2z to the 5th, that's z minus 2 times z to the 5th. Z to the 5th plays no role. The determinant of I minus EA is 1 minus 2z. Okay, so each of the following, in summary, determines the others. The determinant of I minus EA, the sequence of the traces of the powers of the matrix, the sequence which is the number of orbits of size n, and the zeta function of the graph. And by the way, these, what is the sequence pi of n in terms of the graph? Well, if we have a minimal loop, that will correspond to an orbit in this shift to finite type. And so the number of minimal loops of size n is going to be divided by n is going to be this number pi of n. Okay. So now we have, let's go on to see that the same formalism works just as well for graphs labeled by, well, let's just say for the moment with labels from G, and their adjacency matrices viewed as elements over Z plus G. We'll see what these things are. Okay, so again, we're allowing multiple edges between vertices. Last week in lecture 2, I considered label graphs. There were no multiple edges. We didn't need them then. Now we do. Okay, so given a label graph, I'll let G, I'll let G1 denote its unlabeled graph. And A1 will denote the adjacency matrix of the unlabeled graph, and some matrix A is going to present the labeled graph. We'll see what this is in a little bit. The adjacency matrix of the supporting unlabeled graph will be A1 then. Okay, if we have a path of n edges, the weight of the path will just be the product of the labels. So again, I like a simple example. Suppose I have 1, a matrix 1, and A1 is 1. What does that mean? Well, there's just one vertex. It's a 1 by 1 matrix. There's one loop. This is telling me what this unlabeled graph is. And, well, I see that the entry is 1, and so the label is going to be 1. So for each n, there's one loop of length n, and its weight is 1 times 1 times 1. It's just 1. Okay, so another example. Suppose we have 1/2 plus 1/2. Now, with this B1 equal 2, I'm saying that there are two loops. Each loop has a weight 1/2. Okay, so for a given n, there are 2 to the n loops of length n, and each has weight 1/2 to the n. Okay. Now, the total weight of the lengths of the loops of length n is 1, just as it was in the even more trivial example that we saw before. Sometimes we only care about the total weights. And, but sometimes it's important not to know only that, but to also know the number of, sometimes you only care about the total weight of the number of loops. Sometimes we need to know how many loops there are and what is the distribution of weights on the loops. Okay. And so there's a simple algebraic device which handles this perfectly, which I learned from Perry and a paper of Perry and Tungel years ago. Not quite in the same language I'll give. So here's this simple algebraic device. Now, note we're assuming that we have a way to define weights of paths by multiplying labels. Okay, so at the very least, we need these labels to lie in some semigroup so that we have some kind of operation. That's actually never a problem. If there's no semigroup to begin with, you can just take the semigroup of words you get by concatenating labels. And when the semigroup is given as a multiplicatively closed subset of a ring, as it was in the first two examples where we're multiplying positive real numbers, then it's natural to refer to multiplying labels as this group operation. Okay, this semigroup operation. So, you know, a lot of what I'm going to do works perfectly well for semigroups, but just to keep things more simple, we'll let G be a group. So let's keep in mind the example that we were just looking at, which is the example in which G is the group of positive real numbers under multiplication. Okay, so the labels are in that multiplicative subgroup of the real numbers. Okay, but we'll formally define the integral semigroup ring ZG. Okay, so as an additive group, ZG is the free abelian group on a certain generator set. The generators are essentially the elements of G. Just to clarify what definitions are, it's convenient to put a little bracket, put brackets around G rather than just write G. Then an element of this additive group is a formal integral combination. It's just a sum, n sub G times the generators, where the coefficients are integers, and the generators are whatever they are. And to make this well defined, we require that only finitely many generators have non-zero coefficient. So multiplication is going to be forced by requiring the following, what should this be? Well, the group structure should come into play. So, the product of two generators should be, the corresponding generator. Once we require this, then the rest is forced by the distributive law. And I've written here what the distributive law tells you following that. So that's quite natural. This is how it goes. So if E is the identity in the group, then, its generator is the multiplicative identity in the group ring. And we tend to write that as 1. Okay, so now with this in mind, for G, the positive reals under multiplication, we can more precisely write the matrix B, which is presenting this graph. Okay, now we don't write 1/2, but 1/2. Instead of thinking of 1/2 as a real number, we think of it as an element of this group ring and write B as this matrix. And this matrix, okay. So the matrix I was calling B1, that's the matrix which is telling me that there are 2 loops in this graph. How is that related to this? Well, it's the image under the map induced by the augmentation map from the integral group ring to the integers. This map, how do we define this map? If we have a formal integral combination of the generators, we just take it to the sum of those coefficients. Okay, and okay, now let's consider the case that our group G is contained in a ring R, and the group operation is the ring multiplication, which again fits our example. Well, of course, we can then define another matrix, B sub R, which is the image of B under the map, which is defined entry-wise by the ring homomorphism from ZG to R, given in the most natural way. We have this integral combination of generators. Well, the G's were just in the ring, so we just regard those generators as elements of the ring, and then that's the image under this homomorphism. Okay, so in general then, for a matrix over ZG, I guess if I'm thinking about these graphs, there's a little bit more going on here than with Z, because I'm taking non-negative integral coefficients. Okay, and but in particular, though, such a matrix does have its entries in ZG. And this matrix A, I guess, is the matrix B. So if we take the image under the augmentation map, we recover the number of paths from I to j of length n for every I, j, and n. On the other hand, if we take the map described into the ring and we look at the nth power of the matrix, which is the image under that map, then we get the total of the weights of the paths of length n from I to j. And if we just stay with our matrix B, then we get this matrix will encode the number for every n, every I, and every j. B to the n of ij will be encoding the number of paths of length n from I to j and the distribution of their weights. Okay, so this is the elementary algebraic device which keeps track of everything. Okay, so now we can look at the zeta function for a label graph. Okay, so now we need to assume that the group is which is labeling the graph as an abelian group. Okay. Then the integral group ring will be commutative. Let A be the adjacency matrix of the G-labeled graph. Okay, we just defined it. It has entries in the integral group ring. Well, now we can write down the same formula that we already wrote for the unlabeled graph. Same formalism. The reciprocal of the determinant of I minus ZA is going to be this zeta function of the label graph, which, again, is encoding all the information that we were just describing. Okay? So this, once again, we have a finite piece of information, just the list of coefficients of this polynomial, which is encoding a lot of complicated information. Now, how does this proved? Well, I was really belaboring the proof earlier. The proof is exactly the same. Just go and see that you didn't need anything more. We're just working with a different commutative ring. Okay? So let's look at an example. If I take A, again, 1 by 1, the entries are generator for 1/3 plus generator for 2/3 in the reals. Now, it's like this earlier example, but the labels are 1/3 and 2/3. And the trace of a to the n is just the sum n choose k, 2 to the k, over 3 to the n generators. Okay, now let's belabor another point. So why should G be abelian? Well, of course, I was using determinants, so I better have it a commutative ring. But it's kind of worth noticing that things are even worse. We were using these formal power series identities. I was waving my hands and saying everything will be OK. But these underlying combinatorial identities involve some reordering, which may not be justified if we have a non-commutative ring. Now let's see that we can really, and these can fail. And in fact, if you're looking at a non-commutative ring and you're trying to understand the sequence of traces of powers of a matrix, this is a lot worse. This is pretty nasty business. Let's look at a way that we can see that there's trouble right away. We were relying pretty heavily on the exponential, and the identity e to the a, e to the b is e to the a plus b. Now, in any ring, a plus b is equal to b plus a, right? But on the other hand, if a and b don't commute, then we have no reason to believe that e to the a times e to the b is e to the b times e to the a. Okay, so things break down quite badly. All right. Okay, so here's part 3. Here I want to, again, show something that's pretty elementary, at least at the beginning, meaning today. And this is to show how polynomial matrices can be used to present non-polynomial matrices. This is elementary, very, very useful fact. Okay, well, let's start by seeing how a square matrix with entries which are polynomials with non-negative integer coefficients can be used to define a directed and unlabeled graph, let's say GA. And I'm using a variable t now to suggest time. So I have an example. A is t squared, 2t plus t cubed, 0. And I have an instruction to myself to draw the graph for this. Okay, well, okay, it's a 2 by 2 matrix. So I'll start out with the vertices 1 and 2. I see that the 1, 1 entry is t to the 1, so I'll draw a path of length 1 from 1 to 1. The 1, 2 entry is t squared. Now there's going to be a path of length 2. It takes a time of 2 steps to go through that path. Well, there's another vertex in between. It will have no other incoming and outgoing edges except for those which are already drawn. Coming back, 2t, that tells me there are 2 paths of length 2 from t to 1. And then t cubed gives me 3 paths. It gives me 1 path of length 3. Okay, so that's the correspondence. Okay, now this is no longer a 2 by 2. The adjacency matrix of this graph is not going to be a 2 by 2 matrix. There are some extra vertices that have been drawn in. This will be a 5 by 5 matrix in this particular case. And there's some choices of index for these new vertices. They won't matter, so we'll ignore those choices. Okay? And you can see, however, that if I'm allowed to use polynomials, the degrees of these polynomials, could be very large. The coefficients could be very large. So in small matrices, I have the potential for presenting many, many, many directed graphs for constructing many examples rather concisely. Okay? And let me just indicate that that conciseness really does come into play. I'll cite a couple of theorems to indicate just the beginnings of this. So first there's a theorem of Handelman. Okay, I have half an hour. Okay. And it's that the following conditions on a positive real number are equivalent. So the first condition is that there's a 1 by 1 matrix A, a 1 by 1 matrix, such that this A sharp, the adjacency matrix for the corresponding directed graph, is primitive and it has a spectral radius lambda. Okay, so just exactly what spectral radii can we get from matrices A sharp that are arising from 1 by 1 polynomial matrices? Well, of course, such a lambda has to be a Perron number. And is there any other constraint? Yes, there is. The root of the minimal polynomial of lambda cannot have any other, no other root of the minimal polynomial of lambda can be a positive real number. Okay. And that's actually an easy condition to see. But the strength of the theorem is that there's no other condition. Okay, so that's a lot of numbers. Okay, well, suppose we go to 2 by 2. Okay, well, there's the theorem of Perron. He pointed out that the following conditions on a positive real number equivalent. Lambda is a Perron number. Lambda is arises as the spectral radius of A sharp for some A sharp coming from a 2 by 2 polynomial matrix. Okay, so if we go to the 2 by 2 case, we see all Perron numbers. And in fact, you can take this A sharp such that it's primitive. Okay, so in 2 by 2, we see all of that. Okay, now, so far this is just saying that we have something that's rather concise in terms of presentations, but there will be more going on than just conciseness. So let's get an indication of this. So suppose, again, we have A, which is square. It has its entries, which are polynomials with non-negative integer coefficients. And, well, I've written this as t times z plus t because, t to the n is telling me that there's a path of length n. If I have a constant term, that would be t to the 0. That would be a path of length 0. That causes complications. Sometimes it's useful to have those up to a point, but let's not worry about that here. Okay, so anyway, so with this matrix, here's a theorem of Bloch, Guckenheimer, Mizarevich, and Young of some years ago in their paper on the giving a proof of the Sharkovsky theorem. If we take this polynomial matrix, okay, well, we can compute the determinant of I minus A. Fine. Now, well, we also have this A sharp, right? A sharp is what's already known to us as a description of this directed graph. Okay? We already know that the determinant of I minus t A sharp, that's basically encoding this sequence, which is telling us, it's encoding the information of how many loops of length n there are for all n. Okay, so that's the periodic information. And this theorem is telling you that this periodic information is already computed just by that matrix A. You don't have to take A, blow it up into A sharp, do some ugly computation. It's already there as the determinant of I minus A. All right. And for a proof, mañana. Let's look at an example. Suppose we have, I'm really into 1 by 1 matrices today. Suppose that A is the 1 by 1 matrix T cubed. Okay, well, I think we can see how to draw the graph for T cubed. We start with one vertex, right? And then we draw a path of length 3 from that vertex to itself. Okay, so the adjacency matrix here is just a permutation matrix for a cyclic permutation of 3 elements. Okay, and well, the characteristic polynomial of that matrix is T cubed minus 1, third roots of unity. If I write it backwards, I have 1 minus T cubed. So the determinant of I minus TA sharp is 1 minus T cubed. And, well, 1 minus T cubed is indeed the determinant of 1 minus T cubed. Okay, so it works there. By the way, as a side remark, you may notice you get this permutation come in. And sure enough, in general, if you plug T cubed in for T, you'll be slowing time down by 3. Okay, here's a more complicated example, not very much more. So there's A, which is T plus T squared, T, 0. What's A sharp? Well, what's the graph? So A is telling me that I have an edge from 1 to 1, an edge from 1 to 2, a path of length 2 from 1 to 2, and a path of length 1 coming back. I guess in this case, I don't have to think too hard about the name of this new vertex. And we can write the adjacency matrix A sharp for this directed graph, and there it is. Okay, there's one edge from 1 to 3. There's an edge from 3 to 1. From 3. This should be from 3 to 2. So this is a erratum here. 3 to 2, not 3 to 1. Anyway. And then if you correct the erratum and do the computation, which clearly I didn't do because I have faith that it's true, you can see that computation. You can see an example. Okay, now, okay, so we had this kind of polynomial formalism. It's starting to look pretty good. It's determinant of I minus A is capturing the non-zero spectrum, this path information for the unlabeled graph. Now, we can also look at other rings. So suppose A is a matrix over, now with, again, is a polynomial matrix. But now the coefficients are in the integral group ring, where G is the abelian group. Okay, well, just as we can associate a matrix which was a matrix over just as we could associate to the matrix A, which had polynomial entries with integer coefficients, we could take that matrix and produce an unlabeled graph. When we have this integral group ring giving the coefficients, we can associate to the matrix a labeled graph. So let's, I think again with just an example you can see how to do this. So let's look at a matrix which is, let's say, G T GT squared plus H let's say k 2k t cubed. Okay, well, to draw the unlabeled graph, I just regard every g as 1. I look at the matrix, which is the image under the augmentation. So I'll have one path of length 1 from 1 to itself. I'll have a path of length 2 for this term, from 1 to 2. Path of length 1 for this term, forgot to write t, for this term h. And I have, oh, I don't want to write so many letters, so I have two paths of length 1 from 2 back to 1. Okay, now what about the labeling? Well, in the end, what I really care about is the weights and the weights on loops. And the coefficient is going to tell me what the weight along this path is going to be. So for the first, gt tells me I label this edge g. What about 2kt? Well, this is two edges of length 1, and each of them is labeled k. Okay. What about ht? Well, the same old story. Okay, now what about gt squared? Well, all I really care about is that the product of these two labels is going to be g. And to be definite, I could decide that I'll always label the first edge with g, and I'll label other edges 1. And if you like, you can remember that 1 is the same as, 1 is just the identity in this integral group ring. Okay, so this kind of a matrix lets us draw a labeled graph very easily. Okay. And well, now for this label graph, just as for the unlabeled graph, we could write down the adjacency matrix. Likewise, we can write down the adjacency matrix for this label graph. Okay? And because we're looking at the label graph, this is going to have entries which are in the integral group ring with non-negative coefficients. Okay. And now the same thing that worked in the unlabeled case works in the labeled case. The formalism goes right through. The same theorem that we wrote before is still true. It's just now that A involves polynomials with coefficients in the integral group ring. A sharp has the entries which are just in the integral group ring itself. Okay, so the formalism is doing great, and this A is now a very concise formalism for presenting many label graphs in a short way, and we can compute quite easily with that expression the periodic information. Okay, and the proof for this will be as easy as the proof in the z case. Okay, so let's go. Remember something we were thinking about last week, loop graphs. So we used a polynomial or a power series with coefficients in Z plus to define a loop graph with some adjacency matrix A. Well, when f is a polynomial, this is just the same construction we were just doing right now. Okay. Now, when f is a polynomial, this theorem of Bloch, Guckenheimer, Miserevich, and Young tells us that the zeta function associated to this unlabeled graph is the reciprocal of 1 minus f of z. That's what their theorem was telling us. Okay. And well, now once we know that this is true for a polynomial, it's going to be true for a power series. Okay. Why? It's just formal power series again. If f has infinitely many coefficients, if infinitely many terms, it's an honest power series. Well, why should this be true? Well, if we consider, what does it mean for this to be true? It means that there's an equality of power series, formal power series. It means that the nth coefficients on the left and right must be the same for every n. But on the left side, we're looking at the geometric series with f plugged in. So the terms of f which have any contribution to the coefficient of z to the n on the left will be terms f sub k, where k is less than or equal to n. Okay, so we're really just looking at the terms that come from the polynomial case. And likewise, on the right side, if we take an entry here which involves a higher power of z than a given n, it has no contribution on the right side to the coefficient of z to the n in the exponential. Okay, so once we have this formula for polynomials, it immediately follows for power series. It looks very elementary here. It is very elementary, but more complicated proofs have been written, and even incorrect proofs have been written to prove this fact, which even though there's nothing to it. Okay. Now, it's also kind of interesting to note in this special case that this series, you remember in lecture 2 last week when we were looking at an infinite non-negative matrices, we looked at some base index. We looked at this function f, which was given by the number of first f sub n. F was a power series, just as we might be looking at here. F of z was the sum fn z to the n, where this was the number of first return loops back to that chosen base vertex. And then we had a functional relation, 1 over 1 minus f of z was related to this power series, which we were referring to as t, where t sub n was the number of return loops, not necessarily first return loops, back to the chosen base vertex. And there was this elementary but quite important relation between f and t. And this was these played a central role in this theory of the non-negative infinite matrices. This kind of this equation is also fundamental in renewal theory. And it's kind of interesting to see that this 1 over 1 minus f is suddenly arising with this interpretation as a zeta function. So here we have, in this special case, some kind of direct combinatorial meaning for these t sub n. In general, for the zeta function of a finite graph, say, there's not such a direct combinatorial interpretation of the coefficients t sub n, but in this particular case, there is. Okay, so, well, I'm a little faster than I thought, but I think I'll resist the temptation to break into the beginning of a new topic. And so in conclusion, thank you for your attention. I hope this has been of some interest to you, but if this approach to zeta functions has not rocked your world, you can guess why. You still have reason to hope